Starting in 3, 2, 1. So when stars are born, they acquire a tremendous amount of axial angular momentum. And those stars that spin with a lot of angular momentum are white dwarfs. And they expand outwards into blue dwarfs, which then continue expanding outwards into blue giants. And blue giants, the majority of the ones we see in the night sky are pretty obvious because they're so large and they're so bright. Those are the very, very young stars. And they sort of misrepresent the whole stellar populations because they're so young, they're so big, they're so hot. We see them very easily. We think, well, those are the majority of the stars. They're so large, they're so bright. And that was the viewpoint that a lot of early astronomers took, is that, the stars you could see are the ones that are stars. And if you can't see it really, we can't really see it. There's nothing to explain. And that was the mentality back in the late 1800s, is when they were classifying these objects into specific groups, you had different colors of stars, and then they try to think of a color diagram and think, here's all the colors of stars, and this is where they are, and this is the classification of them, and there was kind of a race to classify them all. And then, as our telescopes got better and bigger, we started finding a lot smaller, dimmer objects, and those are the red dwarfs. Those objects that are very, very, very dim. You can barely see them, but we started to see them with our newly advanced telescopes, and we just invented the M classification for those stars. And time goes on, and telescopes get better and better and better, and then eventually we ended up seeing what are called brown dwarfs. And brown dwarfs, they radiate very strongly in a thermal spectrum. Of course, you wouldn't be able to see those very well with a optical telescope. Maybe you could see them, but they're not going to be very visible. And those are the middle-aged stars, but that's basically the stage of star where you can't see it anymore. If you try to look through a telescope, you need a special infrared telescope to see those types of objects. And then back in the 1980s, they just kept on classifying objects, and then you have your Jupiters. The only reason why we see Jupiter in its current form, which is a late-stage, middle-aged star, is that it's in our solar system. We can see it easily. It reflects the light from the sun. But there are hundreds of trillions of Jupiters all over the universe. And as those Jupiters continue cooling and collapsing and combining the elements into molecules more and more complex as it ages, it just gets older, and its axial angular momentum diminishes until, it reaches gray dwarf stage. Now, when I thought up gray dwarf stage, I was like, what's the color difference between Jupiter and Neptune? Well, Jupiter is kind of brown, and Neptune's, blue. So what color difference is that? Gray. Well, that's basically what it really amounts to. And I predict that there's going to be a lot of gray dwarfs too, just as much as there are Neptunes, just as much as there are Earths and Jupiters. And these objects are older than Jupiter and Saturn-sized objects, but definitely younger than the new Neptune and Uranus aged objects. The gray dwarfs, I would say, are for the most part, between 700 million and 1 billion years old. And once you get to about 1 billion, 1.1 billion, then the objects start to resemble Neptune, where there's a small amount of methane built up in the atmosphere. It's lost the vast majority of its hydrogen already back in earlier stages, and its helium. And even some of that helium is still inside the deep interior, as well as the hydrogen, and it's interacting with other elements. And the hydrogen obviously is interacting with oxygen, making things like water. And the object is continuing to lose its axial angular momentum. So we also have another method for determining how old these objects are, is by the amount of energy they spin with. Because obviously if you spin with a lot of spin energy in the beginning, and it starts to age, think of a top spinning. That top is going to start slowing down, and if it loses mass too, well, obviously the amount of actual momentum is going to diminish too. So not only is it going to spin slower, but it's going to spin with less inertia because of the mass loss. And eventually you get to ocean world stages, and ocean world stages are still a very dense stage. This is a stage where the inner Earth is still very, very small and being crushed. So it's not, the inner Earth isn't the same diameter as it is now. But the magical part happens when that thing will expand outwards, is that the ocean world stage, the oceans will start dissipating, and the inner Earth will start to expand a little bit. And then it will be like, well, no, I don't have all this giant atmosphere that was on top of me back in earlier stages of evolution, so I'm just going to go ahead and start expanding outwards. I don't know if you can sort of tell it from the graphic here, but that's exactly what's happening here. And these oceans are extremely deep, extremely thick, and towards the bottom are extremely, extremely hot. So there's some very exotic states of matter in there. And eventually you get to where the Earth has been expanded outwards as much as it could after the release of that thick atmosphere. And it becomes the stage it is now, with those water oceans still present, and it still spins from earlier stages of evolution. I'm sure if you were to look up why the Earth spins in any astrophysics textbook or astronomy textbook, they say, well, it spins from the energy from the protoplanetary disk, but that's not an explanation. The reason why it spins is because it's a very old star. It still has that leftover axial angular momentum. And the stars that have higher axial angular momentum, well, obviously, they're younger stars. But the astronomers, they sort of got ahead of themselves by classifying only stars as being bright, because of various reasons. But as we all know better, and my listeners know better, that the stars, they are extremely evolved in our system. So evolved that they don't appear as being stars because they no longer shine with their own light. And as you can see here on the graphic, the object is continually going to spin for quite some time, and it's going to lose its atmosphere. And that atmosphere loss is natural. The ocean loss is natural. All the life dying on it is natural. We're looking at a dead star. This is Venus. I don't know if you can see the VE at the very top, but that's what Venus is going to be. Earth is going to be like Venus. And Venus, I have Venus as being between 450 and 750 billion years old. So it's going to take Earth quite a long time. Don't fret. Don't let the global warming propagandists make you afraid. Oh my God, it's going to become like Venus if we don't do something. No. Venus also spins very, very slowly. If you walk on the surface of Venus, if you could walk on the surface of Venus at a regular walking pace at the equator, you could watch a perpetual sunrise. That's how slow Venus spins. It rotates very, 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 very slowly. And as you'll see here, the atmosphere is continually lost until the entire object just becomes a giant, stable surface. And there's no atmosphere, there's just a lot of old rocks on the surface. And these objects number into the hundreds of trillions inside of our galaxy. And they're very numerous, they're all over the place. And we call them moons, and we call them planets, we call them dwarf planets. There are a lot of moons in our system that are just like this, but they're the remains of extremely old stars. If the star has had its atmosphere ripped away really fast, though, of course you could have much younger moons than others. But when you look at Mercury and our moon, it's pretty clear those things are phenomenally old. Far, 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 far older than the Earth. And we're coming up on the phase curve of, let's see, what is that, Mercury. See, Mercury is a lot smaller, and it's just sort of, that D in there is dead star, so it's going to just continue wandering the galaxy. and we don't know what's going to happen to it, but actually we do know what's going to happen to it. It's going to smash into other objects eventually, and it's going to create stuff like asteroids and space dust, if you will. Asteroids of all shapes and sizes, and depending on the collision will depend on how much material is released, and as well to think if there is a collision, it's not going to be able to re-grab the material after it's pulverized. It's just going to continue wandering the galaxy with the same spin that it had after the impact event. So if you're wondering why some specific asteroids rotate like they do kind of fast, well, they're still spinning from when they were created from a large collision event early on in their lives. And that's what asteroids are. They're remains of the cores of dead stars that have been pulverized into nothing. So for astronomers, when they say, well, asteroids were remnants of when the sun was born, that's so very wrong. An asteroid is a piece of the remains of the core of an ancient dead star. So think about that next time when you go to a rock store and you buy a meteorite. You're holding a piece of the core of an extremely ancient star that possibly had life on it, just like Earth. So of course I added that in the Krypton hypothesis, but which is a hypothesis that the cores of dead stars are the remains of stars that had life on them, just like Earth.